Now, the LP model follows some implicit instructions which are automatically incorporated during model formulation. And these are the implicit assumptions that we make because the model is a linear model which has a linear objective function subject to linear constraints. But rarely, if any, are there any linear processes or activities in the world. And even though these assumptions are already incorporated in the model, it is still a good practice to consider these during model formulation to ensure that the linear model, which is an approximation, is an adequate representation of the process in consideration. The first assumption is the assumption of proportionality, which is an assumption of both the objective function and the functional constraints. Proportionality assumes that the contribution of an activity to the objective function and to the left-hand side of a functional constraint is proportional to the level of that activity. This results in terms Cj, Xj in the objective function and Aij, Xj in the left-hand side of the functional constraints, where I represents the resource and J represents the activity. Proportionality rules out higher order terms, that is, variables with degrees other than 1. So essentially, it maintains that the degree of any variable should be equal to 1. So it eliminates model linearities due to higher powers of x and y. However, cross-product terms such as x1, x2 are not prohibited under this assumption. To illustrate the assumption of proportionality, consider that I make a profit of $2 per coffee cup, which means that if I sell 15 coffee cups per day, I could make a total profit of $2 per coffee cup multiplied by the 15 coffee cups that I've sold, which means that my total profit would be equals to $30. However, reality is not so straightforward, and there are associated costs with each of these activities. For example, if there is an amortization of the startup costs, or there is an increase in marginal return due to quantity discounts on raw materials, learning curve effect of workers, longer production runs, etc. Or suppose that the opposite happens, that there is a decreasing marginal return due to, let's say, marketing costs and so on. In either case, the profit could not be directly related in a proportional manner to the level of activity. Hence, in each case, the proportionality assumption is violated. If, however, after considering all the associated direct and indirect costs, the proportionality of profit to the level of activity is still a reasonable approximation, then the LP model can still be applied. The second assumption is additivity, which assumes that every function, whether the objective function or the left-hand side of a functional constraint, is the sum of the individual contributions of the respective activities. In other words, additivity assumes that all activities are independent of each other. For example, if I sell both tea and coffee, the sales of coffee do not in any way influence the sales of tea. So when can additivity be violated? For instance, consider a case when any two products being sold require the same machinery for production. This would require switching production processes back and forth and involve substantial time and costs in stopping production of one product to start the other. This could be represented as joint deduction in the objective function because the overall profit would be less than the sum of their profits. So for instance, the objective function can be made to be something of this sort, where this cross-product term would represent the joint deduction from the overall objective function. The reverse may also be true, where this cross-product term is actually added to the overall profit because of, let's say, some sort of a marketing strategy. The third assumption is divisibility, which assumes that the activity can be run at a fractional level. Suppose that an automobile manufacturing company produces two models of cars, car A and car B. We need to determine the number of car A model and car B model produced per week. That is, we need to determine the production rate of each of these models. Now, the production rate can be in fractions. That is a production rate of 3.5 cars per week, or let's say 4.3 cars per week. And this would be perfectly valid. But if we restrict these values to integers, say in the case of the tea and coffee example, where we can either sell 2 cups of coffee or 3 cups of coffee, then this no longer remains a general linear programming problem. The last assumption is certainty, which assumes that all the parameters involved are known constants. Remember that the parameters are coefficients of the objective function or the functional constraints, such as Cj or Aij or even Bi, which represents the total amount of any particular resource available. In real life, however, this constraint, that is the constraint of certainty, is rarely satisfied precisely, as parameters are approximated from the data available and may change during the model validation phase, which is why it is important to conduct sensitivity analysis after determining a model solution. It is possible, and even common, that none of these assumptions hold completely true for a real life application, which is why it is essential to analyze during the modeling phase whether the approximated model, even when the assumptions are violated, is a sufficiently adequate representation of the real life process before dealing with it as an LP problem. But why do we favor LP problems so much more over other types of problems? This is because the algorithms for solving LP problems are very powerful, so the LP analysis is preferred, at least for the initial result, before refining the results further by considering the same process as a non-LP problem.